I welcome all the students. Today, we are going to learn or discuss the topic 3D scaling and 3D reflection. Okay. In previous sessions, we have covered the point 3D translation and 3D rotation. So today's our topic of discussion is related to 3D scaling, as well as we are going to learn about the point 3D reflection. Okay, these are the two things that we are going to learn today. And after this discussion, okay, we are having the next point of the unit that we are going. Okay, let us start our discussion in understanding what is mean by the three-dimensional scaling or 3D scaling. Already we have learned 3D translation, we have learned 3D rotation. We are already knowing that okay, the transformation matrix we are using for 3D transformation is the general 4x4 transformation matrix. Okay, now the diagonal terms of this 4x4 transformation matrix. Okay, so we are considering only the diagonal terms. Okay, of diagonal terms we are not considering here. So the diagonal terms of the general 4x4 transformation matrix produces the local scaling as well as overall scaling. Okay, the local scaling indicate that I want to scale the object in x direction, in y direction, and in z direction. Okay, so that is what my local scaling. The overall scaling indicate that I must perform the scaling in all the direction x, y, and z in all. Okay, so whatever the scaling factor is applicable, that is applicable to all the x, y, and z. Okay, and that is called as the overall scaling. Okay, but in the local scaling, okay, we are having the choice that I may want to scale the object only in x and y direction, but I don't want to apply in the z direction. Okay, so it is our choice. It is indicate that the local scaling and another is overall scaling. Okay, so the diagonal terms of the transformation matrix are responsible for the local and overall scaling. Okay, so the next point that we are considering, I think we will now directly consider the scaling matrix. Okay, so let us consider what should be used as the scaling matrix. Okay, so the scaling matrix, okay, which is shown over here. Okay, this is my x. X is my original object, which is represented as x, y, z, and 1. And this was my scaling transformation matrix, three-dimensional scaling matrix. Okay, as we have seen, the diagonal terms are used for this. Okay, so I'm having the value a, I'm having the value e, and I'm having the j. Okay, so I'm having this value a, e, g. The a, e, and j, these are my diagonal terms, and this last one having the value 1, as we have learned, this is responsible for the overall scaling. Okay, what it means, suppose I'm having this a value, I put at 1, e value 1, j value 1, and I just decide this value to be 2, overall scaling. So this produces the overall scaling. Okay, and if I keep this value 2, means directly I'm going to double the size of the object, whereas these diagonal terms a, e, and j, okay, so these are the diagonal terms a, e, j, will produce the local scaling, okay, which are responsible for the local scaling, and this is responsible for the overall scaling. Okay, now if we look at the what should be the value of my after multiplication, what value I will get, suppose I consider what should be my x star now, okay, or x dash. So my x dash value will be a into x, okay, e into y, and j into z. Okay, so this is my multiplication factor for x direction, this is my multiplication factor e is for the y direction, and this was my multiplication factor j is for z direction. Okay, now as we have seen already, for translation matrix we may consider the translation factor as tx, ty, and tz. Similarly, for the scaling transformation or for the three-dimensional scaling, it is possible for us to consider this term as, instead of a, e, j, I may consider these terms as sx, sy, and sz. Okay, just to show this, okay, we are having this representation. This is the another representation. This and this transformation matrix is same. only for our understanding. Okay, I have mentioned this as A is nothing but it is my the scaling factor in S direction, that is Sx, scaling factor in Y direction, that is Sy, scaling factor in Z direction, that is Sz, and this is my overall scaling value will be 1. Okay, so this is also we can refer or we can consider as my three-dimensional scaling transformation matrix. Diagonal terms value Sx, Sy, Sz. Okay, and this value is 1. So all these diagonal terms are represented for the 3D scaling. You can find that all the remaining of diagonal terms are having the value 0, 0, 0. You can find it here. Okay, all of diagonal terms are having the value 0, and the diagonal terms are going to represent the three-dimensional scaling. Okay, so this is what the transformation matrix that we are using for the 3D scaling. Okay, so let us continue our discussion. I'm just moving to the next slide now. Okay, now if we want, we are just considering this as an example so that you will understand how the object will, three-dimensional object will look like. Okay, suppose if we want to double the size of the object. Okay, so if you want to double the size of the object uniformly in x, y, and z direction, in all direction I want to put these values to be double, means this is, I can say in other case Sx. So what this particular thing indicate that I want to use the value of Sx, scaling factor in S direction, as well as I want to put the value of Sy, I consider the scaling factor in Y direction, as well as the value of Sz. Okay, I'm considering this value of the Sz scaling factor. All the scaling factor, I want to put this value as equal to 2 because I want to double the size of the object. Getting me? If I want to double the size of object uniformly in x, y, and z direction, my value of Sx, Sy, and Sz equal to 2. Okay. Then considering the equation, okay, so as all of you are knowing that how these values are affecting, so I'm having x dash is equal to x into Sx. I know the formula y dash is equal to y into Sy, z dash is equal to z into Sz. Okay, so these are my multiplication factors. So these two will be multiplied to x as well as y as well as z. So I'm taking all these uniformly, the double the size of the object. Okay, so this is what we are considering. Now, just now I have written over here the same thing. I consider the values of xx is equal to sy is equal to sz is equal to 2. Just now I have mentioned over here as we want to double the size of the object. Okay, so now if I want to double the size of the object, how the object will look like? Okay, just to have the example or to visualize this. Okay, I'm just moving to the next slide. The result of the same, what is the result? Result is to double the size of the object. Okay, that was our purpose. Result is to double the size of the object. Okay, and that was shown in our following diagram. Okay, look at the very simple diagram. I'm having this particular is my original object. Okay, this is my x-axis, this is we consider as the y-axis. Okay, and we are considering this as in the z-axis, x, y, z axis respective. I'm having this the original object, and if I'm going to double the size of the object, okay, so how the object will look like? My object will look like something this. Okay, you can find it as this particular object which is represented into the 3 dimension, and we are going to double the size of the object, and here I found the object is, okay, so this particular object, okay, so this one indicate me the doubling the size of the object or as per the original object. So this was my original object, and after scaling, after doubling the size of the object, I will get this is my correct answer. Now you can find the object has also translated. The reason is I'm doing all this three-dimensional scaling with respect to my origin 0, 0, 0. Okay, getting me? So I'm not doing the scaling, okay, from a fixed point or from a arbitrary point. I'm doing this scaling with respect to my value, x value is 0, y value is 0, and z value is 0. This is my origin. So with respect to origin, I'm doubling the size of this object, and this was my diagram which is going to represent this. Okay, so a very simple example of three-dimensional scaling, and this will show how the object will look like, three-dimensional object will look like when I am going for doubling the size of the object. Okay, so continue our discussion. Let us understand the next point related to the three-dimensional scaling now. Okay, now we have considered previous example where I have not represented that object in a transformation or in a matrix form. Okay, I have just taken it as a very simple object, okay, a solid object, and I have shown that how it will be double the size of the object. Okay, now but understand this type of the scaling in detail. Now I am considering another example where I am considering the rectangular parallel pipe. Okay, I'm considering rectangular parallel pipe as shown in the diagram. Okay, let us consider the diagram of the rectangular parallel pipe. Now I think this will be the object, okay, that will be very easy for us to understand. Okay, and now we can go for the three-dimensional scaling of this object. Okay, consider this is my original object, which is a rectangular parallel pipe. Okay, now you can find it is having, so this is my x direction, this is my y direction, this is z direction. Okay, so this is my original object, and it is represented with the help of the transformation matrix, and I can represent it is having the 8 points a, then this is b, we are having this point as c, and this is d. Equivalently I'm having the value e, f, g, and h. Okay, so these are the points of my original object which I want to scale. Okay, now how this a b c d e f g h will be represented, because we have seen the three-dimensional transformation matrix or scaling matrix. Okay, three-dimensional transformation in the scaling type of the matrix. So I must have the matrix representation of the original object. Okay, original object should be represented in the matrix form. So let us consider how this particular object will be represented in a three-dimensional matrix form. Okay, so this is what I'm having. So this is my x. What is this x? X is represented by, this is my object x. Okay, original object x. How it is represented? It is represented with the points or vertices a b c d e f g h. Okay, now this is the representation. Obviously all of you are knowing this is my x value of the object. Okay, this is my y value of the object. This represents the z value, and obviously this is the h homogeneous factor h value represented. Okay, and all of you are already knowing these points I have represented as the value of a. Okay, so this is the value a is represented, this is represent the value b, this will be c, and so on. Getting me? So this is my a b c d e f g h, all these values are there, all the points are represented in the, or the, we can say this is my homogeneous position vector representation of my original object rectangular parallel pipe. Getting me? Now just consider as an example, what should be the value of a now? A is having the x value 0, y value 0, z value 1. Let us consider whether it is correct. See, what about, this is my a point. Okay, what is the a point x value? Yes, it is 0. Correct. What is the y value? Yes, it is also 0. Correct. What is the z value? Yes, in the z direction I'm having, it is having the value 1. So z value is 1. It is correct. It is correctly represented. Okay, so let us take one more example of, suppose I'm taking the representation of the c point, this particular point. Okay, so I take this as my c value. C, what is the x value? X value is 2. So I'm having this x representation, this is 1 and this is 2. Getting me? So this is 1 and 2. What is my z y value? It is 3. So here I am having the y is divided into, this is, suppose this is 3, this parameter is 3. Somewhere I am having the value this as 1 and this as 2 and this is 3. So y is represented and having the scale of 3, and x is having the scale of 2, and z is having the scale of 1. Yes, 2 3 1, and that is represented by my point c. Okay, so c point is represented by x factor or x scale is 2, y scale is 3, and z scale is 1. Okay, similarly I have represented all the points. Okay, so all of you have understood how this object is represented in the transformation matrix form. Okay, Now I want to perform the three-dimensional scaling on this particular object. Okay, so that it will be easy for me to show that how I want to do it. Okay, now my next slide I'm showing this result, but now suppose, okay, I say I'm just considering that what is the maximum displacement of this object in z direction. Okay, what is the maximum displacement of this in z direction? It is 1. What is in y direction? It is having 1 2 3. So maximum displacement in y direction, it is 3. And what is the maximum displacement in x direction? You can say it is 2. Getting me? So x, it is having maximum displacement of 2, the y, it is having the maximum displacement of 3, and the z, it is having the maximum displacement of 1. Okay, so in this particular case, okay, so I'm having the value x, y, and z, okay, in this displacement. Now my three-dimensional scaling, with the help of three-dimensional scaling, suppose I want to convert this rectangular parallel pipe into the unit cube. Okay, I want to convert it into unit cube. So unit cube is having all these x, y, z value 1 1 1. Okay, because it was a unit cube. So I suppose I want to convert this rectangular parallel pipe into a unit cube. So what I need to do? Okay, my z value is 1, so my scaling factor will be 1. What about y value? Y value is having the scale of 3, so I must divide this y value by the scaling factor sy, which is 1 by 3, because 3 divided by 3 I will get this 1. What about x value? X is 2, so I must divide this or multiply this by 1 by 2. Okay, so 2 divided by 2, it is 1. Then I can convert this into the unit cube. Okay, so let us understand this with the help of the example. Okay, so I'm just moving to the next slide to understand the three-dimensional scaling. Okay, now here I'm having the example of the same, okay, which is my three-dimensional scaling. Okay, so what is the first point I have represented here is rectangular parallel pipe. So this is shown in the diagram A. So this is my diagram A, which is my original object, which is a rectangular parallel pipe, is scaled on converted or scaled on converted into the unit cube. So I'm going to scale this particular object. Okay, this particular object I'm going to scale so that it will be converted into a unit cube. It is converted into a unit cube as shown in the diagram number B. Okay, so I want to achieve this with the help of this. Okay, so as I have already told, what should be my value of Sx? X is having maximum displacement 2. What is my x value? It will be 1 by 2. So I'm having Sx is equal to 1 by 2. I'm having the value Sy is equal to 1 by 3, because maximum y displacement is 3 and I want to make it to the 1. So I want to compress this object through y direction so that instead of 3 it will come to 1. Okay, so this will becomes here. Suppose I consider this value is 1, this value is 2, this value is 3. This is my 1 2 3 value. So this I want, this is my 1 value, this is my 2 value, and this is my 3 value of y. I want to convert it into only 1. Okay, I want to convert it into only 1. Getting me? Okay, and what is my Sx value? In x direction it is having, suppose this is my 1x value and this is my second value x is 2. So again I want to compress it so that it will be reaches only to this and not more than it. And what about z? Z is already 1, so I divide sz scaling factor is equal to 1. So my sx is 1 by 2, my sy is 1 by 3, and my z is 1 as it is. Then what was my result after performing three-dimensional scaling? I will get this diagram as a B, and this was my transform object. You can find this transform object is having the value a star, a, b, c, d, and all this is converted into the unit cube. Okay, I have converted it into the unit cube and I have performed the local scaling of this. Okay, why I'm saying it as local scaling? Because the fact values of sx, sy, and sz are different. They are not same. Sx is 1 by 2, sy is 1 by 3, sz is 1. Why I have selected this sx is 1 by 2 and sy is 1 by 3 and sz is 1? Because I want to convert this rectangular parallel pipe into a unit cube. Okay, I want to convert it over here, or I want to convert it into this. Getting me? So due to this reason, okay, so I have shown this as the example of the local scaling, where the value of sx, sy, and sz are different. Getting me? Now in reverse case, I continue with the same example to understand or to consider that how my 3D scaling will look like. Okay, now consider my object is shown in the diagram B, which is the unit cube. Okay, and now I want to convert this object into this particular object. So this is my 3-dimensional scaling, and now I want to double the size of the object. Getting me? So what was my purpose now? My purpose was to double the size of this particular object. I want to double the size of this object. Okay, now in that case I have shown this into the this diagram B is the unit cube is converted into diagram C, and diagram C is the doubling the size of the unit cube. Okay, so that is what we have shown. Now what we are doing now, the unit cube is shown in the diagram B is scaled again to double the size of the object. I want to double its size, and the resulting diagram is shown over here. I want to double the size of the object. So doubling the size of object may be considered as overall scaling, because in all x, y, and z direction I want to double the size. Okay, if I am considering this scale is 1 and this is the 2 scale, then here you can find my x value is this is 1, this is 2. Y value, this is 1, this is 2, correct? Z value, this is 1, this is 2. Means all the direction I am going to scale this object, this unit cube, and this is my object after doubling the size of the unit cube. Okay, so I consider this was the diagram or the example which have cleared your concept of the how this 3-dimensional scaling is applied on the different object. I think we have shown the transformation from A to B. Okay, and I'm calling this as my local scaling because I'm having the value of sx, xy, and sz are different. They are not same. Whereas I'm considering the transformation of the object or unit cube B into C diagram, which I call it as the overall scaling. Okay, in all direction, I'm going to scale the object and I want to double the size of the object. Okay, so this will clear your concept of the what is mean by the 3-dimensional scaling. Okay, so we are now continuing our discussion, okay, to understand the next point of our today's discussion, okay, today's session. Okay, now what we are going to do here is, we are going to learn the 3D reflection. Okay, so I'm going to do here, I'm going to learn the 3-dimensional reflection. My point of discussion was nothing but it is 3-dimensional reflection. I'm going to learn 3D reflection here. Okay, so let us understand the 3-dimensional reflection. Okay, in 3D reflection, okay, I'm just putting this point. In 3D reflection, it occurs through a plane. I think we have learned in 2-dimensional reflection, it occurs about x-axis, about y-axis, through z-axis. Okay, now here we are having it reflection occurs through the plane, means about z-axis means about xy plane, and so on. Okay, so that we are considering here. Now, one more important thing that we have to consider is for a pure reflection, okay, for a pure reflection, the determinant of the reflection matrix is identically -1. Okay, the determinant of the reflection matrix should be -1. That we have to remember. Now, let us consider in reflection through xy plane. Okay, now we are considering the first type of reflection. I consider the reflection through the xy plane. If I'm going to reflect the object through xy plane, only the z coordinate values of the object's position vector changes. Okay, only the z coordinate value of the object vector will be changes if I'm going to reflect the object about xy plane. Very simple. In fact, the z coordinate values are reversed in sign. Okay, so these values are change reverse to the sign, means the sign will be changed to minus. Okay, it is plus, it will be minus, it is minus, it will automatically plus. So we are going for the reversing the sign. Okay, so now I'm just considering what should be my transformation matrix. The transformation matrix for reflection through xy plane is, transformation matrix for reflection through xy plane is, yes, this is my transformation matrix T. You can find, as I told, this value is my x, this value is my y, this value is z, and this is for h. Similarly, I am having this value is x, this value is y, this value is z, and this is related to h. Now, as we have seen or we have written here, the reflection through xy plane, only the z coordinate value of the object changes. All remaining values will not change. So what is the x value? It is the 1. This is y value, this is 1. What is the z value here? I find that z value only is -1, because I'm going to reverse the sign of this, and h value is equal to 1. And that is, if you can look at this, the reflection transformation matrix, x, this is 1, first diagonal term, second diagonal term is 1, z, okay, this is z, row and column, z and z, I get this value as -1. This is diagonal term is 1, all remainings are 0 0 0. So that's why I think we can prove here the we have added this sentence: for a pure reflection, the determinant of the reflection matrix identically it is -1. Okay, if I consider this, I will get the determinant of this reflection matrix, and I will get the value is equal to -1. Okay, I hope all of you understood the reflection through xy plane. So here in three dimensional, we cannot call the reflection about x-axis, y-axis or z-axis, but we call it as the reflection through xy plane. So reflection through xy plane indicate that only the z value will be -1. Okay, so that we have to remember. Okay, so continues our discussion with the reflection about the xy plane. Okay, consider that now we are concentrating on the 3D reflection. Okay, and we have considered about the unit cube. Okay, now we just look at how this reflection of a unit cube through the xy plane is shown. Suppose I want to perform the reflection of the unit cube through xy plane. Okay, so how I can perform this? Okay, now here I have represented is the transformation matrix. The transformation matrix for reflection through the xy plane is given by the equation. Okay, so now what we are having, my x star, x transform object or reflected object x star is equal to x into t. Okay, what is my x? This is my x value, which is a representation of a unit cube. So unit cube is represented with this. We have already seen some of the example of the unit cube representation. So this is my representation of a unit cube. Okay, and what is this? Okay, this is my transformation matrix T, getting me, and which is used for the reflection through xy plane. We have seen reflection through xy plane. This is 1, this is 1, this value only is -1, which is represented for the z. Okay, reflection through xy plane means only the z value is reverse, or it is -1. Okay, and if I multiply this and this, okay, you can find that here I am already having the, okay, unit cube which is represented, I'm already having its value. Okay, so already I'm having the value of z is minus, okay, -1, -1, -1, -1, -2, and so on. Okay, we will see the diagram of this also. So if I multiply this with this matrix, this is minus into minus, I will get this value as 1. So I will having in the reflection, if original value of z is minus minus minus, I will get the after transformation the values of the z as 1 1 1 1. Okay, so this is what indicate the three-dimensional reflection, how the transformation, how the matrix representation of a 3D reflection through the xy plane. Okay, so we have, I hope all of you understood how the matrix representation is there for this 3D reflection about xy plane. Now let us understand or consider one diagram which will make you, or which will make the concept more clear. With the help of the diagram, we can see how this reflection will be displayed. Okay, now understand the example here. The reflection of a unit cube through the xy plane is shown as below, or I say it is looked like this. Okay, how it is look like? My question is how it look like. Okay, let us consider that. What is my original object? First I have to find out what was my original object. See, my original object, okay, my original object for the reflection is this. This is my original unit cube. Okay, this original unit cube is having the values, z values, which are minus. It is already having the z values which are minus. And now I am considering this is my z value, which is up to this, it is positive. You can find it as here. Suppose this is my 0, 0, 0. Okay, and in this direction it is minus z value. Okay, it is minus z value. And this is what my angle of reflection. See, I'm going to reflect this original object about xy plane. Okay, what I said, I'm going to reflect this object about or through xy plane. So this is my, I consider this is my x plane and this is my y plane. Okay, so in that case, the object's z value will be, if it is minus, it will become plus. If it is plus, it will be minus. But in our case, the original object is having z value minus. So I will get, this was my reflected object. So this is my object after reflection. Okay, so this diagram shows that this is my reflection of a unit cube through the xy plane. Okay, through xy plane, I will get this value, and this is my, see, this is my x, y and x plane, or we call it as x and y plane. So consider this as the angle of reflection. So that's why this will be reflected over here. Okay, and about z axis. Okay, so z axis is going to change. Original object, what is the z value? It is minus or minus 1. Here I will get this z value to be plus 1. Okay, and this is what the diagram or the example of the three-dimensional reflection. Okay, so I hope all of you understood the three-dimensional reflection. We have considered the reflection of the unit cube about the xy plane. I think there is no need to consider the reflection about all remaining planes. Okay, but at least what we are going to do, or at least what we are going to consider is, we are considering the three-dimensional reflection. Similarly, as xy plane, I consider for the yz plane or xz plane also. Okay, so I'm just moving to the next slide to consider the transformation matrix for this. Okay, so let us consider the point. Now, the transformation matrix for reflection through yz plane. Okay, so if I'm considering the transformation matrix of the reflection matrix through the yz plane, it indicates that here it is yz, means x is not there, means only the x value will be minus 1, or only the x value will be reverse, or a sign of the x value will be revert. Okay, so what will be my transformation matrix for this? Yes, this is my transformation matrix T. Okay, you can find it here. This is my x value. Okay, this is my y value, this is my z value, and this is h, which is used for the homogeneous coordinate system. So again, I consider this is x value, this is row wise, this is x, y and z, and this is h value. You can find it here. What is the reflection? The reflection through yz plane indicate that the x value will be minus 1, and that is represented here. X will be minus 1, y value, y value will be 1 diagonal term, z diagonal term is 1, and obviously h is 1, and all remaining values are considered as 0, 0, 0. Okay, so remember this transformation matrix, which is used for the reflection through yz plane. Okay, similarly, I think only one more reflection is now remaining, and its transformation matrix, that is about xz. Okay, I just continue with the discussion. See, the transformation matrix for reflection, we are considering transformation matrix for reflection through x and z plane. Okay, through x and z plane means what is remaining, or it is not there, that is y. So my y value will be having the reverse sign or the minus sign. Okay, as we have considered. Okay, so what is our expected? Easily, I think everyone can draw the transformation matrix after the discussion. So this was my transformation matrix. Okay, this is the transformation matrix for reflection through xz plane. Okay, again I have said this is my x value column wise, this is y value, this is my z value, this is obviously h value. Okay, it is a homogeneous coordinate system. So this is x, this is y, this is z, and you can find that reflection through xy plane, so only the y value will be reversed or the minus. Then I can finding that the row of y and column of y represented the diagonal term, and you can find this value is -1. All the remaining value diagonal values are 1 1 1, and all remaining values are 0 0 0. Okay, so if I multiply the original object and then with the transformation matrix, this transformation matrix, I will get the reflection of that 3D object through the xz plane. Getting me? So this is what the way we can represent the three-dimensional reflection. See, three-dimensional reflection is about, or it is reflection through the, we can say, we cannot say it is x about x-axis, y-axis or z-axis. We represent it as reflection through the xy plane, reflection through the yz plane, and reflection through the xz plane. Okay, so this is what the and their respective transformation matrix. And we have considered the example how the diagram will look like, how the three-dimensional object will look like, okay, after the reflection through the, we can see it as xy plane, okay, that we have seen with the help of diagram. And also we have seen in this today's session the point three-dimensional scaling, okay, and we have seen the three-dimensional scaling transformation matrix, okay, which was represented as, or the scaling factors, 3D scaling factors we are having is sx, sy and sz. When all these sx, sy and sz value may be different or they are having, I will represent the scaling with the help of sx, sy and sz. I call it is my local scaling, okay, and I may consider it as, instead of local scaling I will also go for the overall scaling, okay. And we have also seen the diagram, okay, as well as the representation of the three-dimensional scaling and its matrix representation, okay. So I hope all the students have enjoyed the session, and we have learned the two very important three-dimensional transformation. One is known as, one of its type is 3D scaling, and another is three-dimensional reflection or 3D reflection. Okay, so with this discussion, we are going to end our session over here. Okay, so I say thank you all the students. Thank you all.